lecture, I kind of hesitated because I never did this kind of a public lecture before. Okay, this lecture is supposed to aim at an audience that is not experts in chemistry, but is otherwise well educated, right? So I thought I will have to strike a good balance between chemistry expertise and general knowledge. And I spent quite some time preparing this talk. Okay, so hopefully you will give me a passing mark for today's lecture. Okay, so thank you for coming to this lecture room, and also thank those who are watching this event online. So the topic, the title of my talk is Catalysis, Changing the World for the Better. There are three parts. Okay, first of all, I'm going to do an introduction to chemistry in general and catalysis in particular. This is followed by a review of the development and impact of chemical catalysis in the last part of the talk. So I'm going to introduce you to my current research, which is known as computational catalysis. Okay, a little bit about my research background. I received training on synthetic organometallic chemistry as a PhD student and a postdoc in America. So I was doing synthesis, So I joked with my students, telling them, I got my PhD by making sandwiches, those metallocarborane, metal organic sandwich complexes, This is the highest sandwich I made. You see a hexadecker sandwich, right? I made it by fusing two triple deckers, It was and still is a world record for its kind. And then after I started my independent research, I worked on metal organic frameworks. About 10 or so years ago, I made a quantum leap from doing chemistry in wet lab, from doing wet chemistry to doing computational chemistry in silico, on a computer. But as I find out, the principles of chemistry are the same, no matter you are doing lab work or computational work. So what is chemistry? There are many definitions, but this one, I think, given by the great Chinese Academy of Sciences is the best one, Here I'd like to share their definition of chemistry with you. Chemistry is a basic science that studies matter and its changing processes at the microscopic level of atoms, molecules, and ions. It is creative discipline based on experiments. So this definition says it all. Oftentimes, you hear people saying chemistry is the central science. What is meant by chemistry being a central science? It means chemistry connects with many other STEM disciplines. STEM stands for science, technology, engineering, and mathematics, right? Including biology, medicine, material science, environmental science, and chemical engineering. Chemistry, the central science. You see, chemistry is here, in the center, right? It acts as like a hub or nexus, connecting all these useful disciplines of science and technology. Next. What is it? What's the difference of chemistry from all these other sciences? So what is it that chemistry can do that other sciences cannot do? What a mouthful, right? But here's the Chinese phrase. It's much easier. 化学的绝活是什么? Huh? Here's the answer. synthesis, okay, or chemical synthesis, okay, 化学合成, okay. It is creating known as well as new substances through the execution of chemical reactions. This is something chemistry, okay, chemistry can do, but other sciences cannot do, okay. This is what distinguishes chemistry from the other sciences, okay. Everything around us has been made, at least in part, by chemical synthesis, okay? All right. This is a generic scheme for chemical reactions. When chemists start a chemical reaction, they mix up known substances, okay, known as reactants, right? Okay, in the hope of making the target compounds, which are other known substances or new substances, okay, that have not been made before, okay? Different chemical reactions proceed at different speeds, okay, depending on the nature of the reactants and temperature and many other factors. For example, okay, the combustion of hydrogen gas in air or oxygen, okay, the explosion of hydrogen gas is done in a split second, right? Very fast reaction, okay? The rusting of iron, by contrast, okay, is a slow chemical reaction, right? So here, okay, people took these real pictures, okay? 2 years later, okay, this iron lab support, okay, became rusted, right? You see, so this is a slow reaction. In this case, it is a good thing, right? To have this slow reaction, you don't want the iron support to go rusting, very fast, right? Okay, but when chemists develop chemical reactions to do chemical synthesis, normally they want their reactions to go fast rather than slow, right? Okay, because they want to graduate in 4 years or in 5 years, right? Okay, they want to make a product, right? Okay, as soon as possible. So that's where catalysis comes into play. Okay, catalysis is the speeding up of chemical reaction by adding a small amount of substance known as a catalyst. The increase in reaction rates by catalysis can be dramatic. Okay, let me give you something, okay? The people in finance know this very well. They took our term, catalysis, okay, and they made their definition of a stock catalysis. Okay, a catalysis is a message or event that moves a stock dramatically up or down. So you got the point, right? That's what the catalysis can do, right? Okay, so that's just digression. All right, now let's move back to chemistry. Go back to chemistry. All right. Okay, a chemical reaction requires energy. Okay, you start from the reactants, right? The starting materials, okay? And the reaction must overcome this so-called transition state or energy barrier to reach the products, right? Okay? This is the energy barrier for an uncatalyzed reaction. Okay, it's pretty high, right? Okay, when you use a catalyst, okay, the catalyst gets involved in the reaction and it changes its pathway. It opens up a new pathway with a lower energy barrier, right? Okay, that's how a catalyst works. Okay, and this cartoon, okay, is because I found this on the internet. Okay, so this is how. Okay, this says about the way a catalyst works. Okay, so without a catalyst, okay, you have to overcome this. Okay, this pretty big hill, right, to get home, right? And with catalyst, okay, the catalyst opens up kind of a tunnel, right? Okay, so you can reach home a lot faster, okay, in a much shorter time. In addition, the catalyst gets regenerated and it goes back in the catalytic cycle. That's why you only need a very small amount of catalyst, okay, to do the work. Okay, why? Because the catalyst provides a platform, on which the reactants A and B do chemistry to form the product C, right? And then generally, okay, in the last stage of catalytic reaction, okay, the product C comes off the catalyst, right? The catalyst gets regenerated, okay, and goes back in the cycle again. So it cycles through, okay? Okay, so here are the important message I want you to take home. Okay, catalysis can make existing reactions easier and faster. Catalysis can allow new reactions that otherwise would not happen because of very high energy barrier, okay? All right, so who discovered catalysis? So in the process of preparing this lecture, I kind of, I dug a little bit into the history of catalysis and learned something new to me. Okay, in the textbook, normally you see this, it's usually attributed to the Swedish chemist Berzelius, who named and conceptualized the phenomena about 200 years ago, He kind of described the concept of catalysis as we know it, better than his contemporaries, So we attributed the conception of catalysis to Berzelius, And this man was he coined, the other reason is he coined the term catalysis. And he was very good at naming things, He came up with all these names in chemistry: protein, 蛋白质, right? Polymer, 高分子, isomer, 异构体, and organic versus inorganic, 有机和无机. Now he came up with all these chemical terms, All right, and then, during the process of preparing for this lecture, I did some literature search, and there are some historians of science and chemistry who argued, this woman scientist, Elizabeth Fullerby should get a lot of credit for describing the concept of catalysis some 40 years earlier than Berzelius. She actually published this article on combustion, in which she described water catalysis, how water is needed and involved in certain oxidation reactions, and how it is regenerated when the reaction is complete. It was essentially the concept of catalysis as we know it. These historians of science believed, she faded away from the history of science because of gender discrimination. She was now considered the first woman researcher of modern science. It was a British or Scottish woman. Anyhow, since catalysis was discovered and conceptualized, it has had a profound impact on the development of modern society. Now, catalysis is used in 90% of industrial chemical processes that eventually make 80% of all manufactured goods. Catalysis contributes to more than 35% of the global GDP, and the Nobel Prize has been awarded 8 times, not 7 times, for chemical catalysis. In addition, there are a few times awarded to biocatalysis, which I will not cover today. Generally speaking, there are 3 pillars of catalysis. These are transition metal catalysis, which is catalysis enabled by using transition metal based catalysts. There's organocatalysis, effected by using organic compounds as catalysts. Okay, there's also there's also biocatalysis. Okay, that is enabled by natural catalysts known as enzymes. So far, transition metal catalysis has been dominant, okay, for a good reason, okay. Where are transition metals? Okay, they are kind of, okay, in the middle of the periodical table of elements. Why do transition metals make good catalysts? Two reasons. Okay, transition metals can activate various molecules that are being catalyzed, okay, by forming complexes with them using the d orbitals, okay, for bonding and back bonding. In addition, transition metals can have variable oxidation states or charges, okay, which can facilitate the transfer of electrons. As we all know, a lot of chemical reactions occur through the transfer of electrons from one substance to another substance. All right, so that's, okay, the first part about a brief introduction to chemistry and catalysis. Okay, now I'd like to walk you through the milestones of catalysis so that you can see the impact, you can see and appreciate the impact and importance of catalysis. Then I figured, okay, a good way of doing that is to take you through through a journey, through the 8 Nobel Prizes that were awarded to scientists who developed various kind of catalysis. Okay, the first Nobel Prize for chemistry was awarded in 1909, approximately 10 years, okay, from the beginning of Nobel Prizes. It went to the German chemist, okay, Wilhelm Oswald. You see, this process, okay, this industrial process bears his name, okay, the Oswald process that was used and is still being used to make nitric acid. Okay, this is the major reason he received the first Nobel Prize awarded for catalysis, okay, for his work on catalysis. Okay, that's the major contribution. Okay, nitric acid is one of the 100 most important chemical compounds. Here's the reaction. It converts. The first step is the reaction of ammonia gas and oxygen in the presence of platinum as a catalyst, okay, to make nitrogen monoxide and water. And then nitrogen monoxide gets further oxidized to form nitrogen dioxide. Then nitrogen dioxide reacts with water to form nitric acid and nitrogen monoxide. Okay, that can be reused, okay, for the further oxidation here. Notice now, annually, there's approximately 60 million tons of nitric acid that is being produced worldwide. Okay, this is one of the most important chemicals. Of course, okay, the reaction was catalyzed by a transition metal catalyst, okay, platinum right here, okay, a transition metal. All right. It didn't take long for the Nobel Prize Committee to award the second Nobel Prize for catalysis to this French chemist, Paul Sabatier, okay, for his work on hydrogenation reactions in the presence of finely disintegrated transition metal catalysts, okay, including nickel, okay, and other transition metals. So what is the big deal about this reaction? So this catalytic reaction converts carbon dioxide and hydrogen gas into methane, okay, CH4, as we all know, okay, methane is the major component of natural gas, right? So this is known as synthetic natural gas, okay? It occurs, the reaction occurs at the surface of the transition metal catalyst. Okay. The third Nobel Prize for catalysis was an exceptional one, okay? The German chemist Fritz Haber got this Nobel Prize for his work. You see the caption here says, okay, Fritz Haber, the best/worst chemist in history. So he was called the best chemist because he developed this catalytic reaction of synthesizing ammonia, okay, the Haber process of nitrogen fixation, okay? He was called the worst chemist. Why? Because, you know, he was helping the German government to start the first chemical warfare in history during World War I, right? Eric, correct me if I'm wrong. Okay. So anyway, this reaction, okay, of nitrogen fixation, nitrogen comes from the air, right? Okay, to make ammonia, okay, is considered the greatest chemical reaction in human history. Not one of the greatest, okay, the greatest chemical reaction in human history for a good reason. Okay, now you see, you know, annually 230 million tons of ammonia is being produced worldwide. Why is it this is said to be the greatest chemical reaction in human history? Here's the reason. Okay, you look at this diagram. Okay, from 100 AD to 1900 AD, you see the global population was growing, okay, but kind of slowly, right? Slowly. And then around the turn of the 20th century, you see, we began to see an exponential growth of global population. Why? It is because of, or largely due to this catalytic reaction developed by Fritz Haber. Okay, that's the reason this was called the greatest chemical reaction in human history. And that's why he was considered, okay, one of the greatest chemists. Okay, why? Because ammonia is the source of most fertilizers. Okay, the fertilizers help agricultural crops, products, which eventually become the food we eat. Okay, according to some estimates, about 50% of the nitrogen atoms in our body come from this catalytic reaction, okay, from synthetic ammonia. Okay, so now we can have good understanding why this is the greatest chemical reaction. Okay. So it took a while for the Nobel Prize Committee to come back to catalysis. Okay, this time, okay, they gave the fourth Nobel Prize for catalysis to these two European chemists, Ziegler and Natta, okay, for their work on discovering organometallic polymerization catalysts. This time, they used the transition metal called titanium, okay, which is the early transition metal here in the periodic table, okay? And this catalytic reaction revolutionized the manufacturing of polyolefins, okay, represented by polyethylene, right? 聚乙烯, plastic, okay, commonly known as plastic, okay? So you see this HD, you see these, okay, lots of these symbols. What does it stand for? HDPE, high density polyethylene, okay? PP, polypropylene, okay, PS, polystyrene, okay, all these polyolefins, plastic materials are made available by this catalytic reaction and its derivatives. Okay, now let me do a little summary. Okay, the first 4 Nobel Prizes that were awarded for catalysis, okay, were awarded for transition metal catalyzed heterogeneous reactions. Okay, heterogeneous means the catalyst and the reactants occur in different phases. Okay, the catalyst is a solid, right? Okay, the reactants are normally, okay, are gases. Okay, so we have there's a physical boundary between the catalyst and the reactants, right? So that is what is meant by heterogeneous. Okay, the reaction actually occurs at the gas-solid surface. Okay, now let's move into the new century. Okay, this is the 5th Nobel Prize for catalysis. Okay, which went to those 3 chemists for their work on homogeneous catalysis, 均相催化. Okay, heterogeneous catalysis is known as 多相催化 in Chinese. Okay, homogeneous catalysis allows a more precise control of products. Okay, in a homogeneous catalytic reaction, the catalyst and the reactants are all dissolved in one solution phase, okay, in liquid solution. Okay, there's only one phase. That's why it's called homogeneous catalysis, okay? And they got their Nobel Prizes because their work on chirally catalyzed hydrogenation reactions for Knowles and Noyori, okay, and Sharpless got the award for his chirally catalyzed work on oxidation reactions. So chiral catalysis is also known as asymmetrical catalysis or 不对称催化 in Chinese. Okay, so I'm going to explain the word chiral in more detail. So chiral means hand, okay? In chemistry, a molecule or ion is called chiral if it cannot be superimposed on its mirror image, just like our hands, right? Our left hand, you know, and our right hand look similar, okay? They're mirror images of each other, but they're not identical. Because you cannot overlay your right hand on your left hand, right? Okay, they're symmetrical, but they're not identical, right? A lot of chemical molecules, a lot of drug molecules are like our hands, or like chiral molecules, and only one mirror image produces pharmaceutical effects, okay? Because our body, the human body, is chirally selective. A lot of chiral molecules inside, okay, in our body, okay? Let me give you a good example. Ibuprofen, okay, 布洛芬, okay, is a chiral drug molecule. This is the R form, okay? There's one mirror image. This, okay, the other mirror image is the S form, right? It is this S isomer that is pharmaceutically effective. Okay, this is what you get from a pharmacy, right? This is actually a mixture of both isomers, which is fine, okay? Because in this case, the R isomer, the R form, is harmless, okay? And you can just get, okay, there's no need to separate the two, which would be, okay, which would add additional cost, right? But in other cases, we do need to remove the image, okay, that is not useful, right? And then you can do separation, which would be costly, and then we can come up with a chirally selective catalyst. We can go straight to the image, to the form that we want, okay? here's a good example. Okay, the trick is to use a chiral catalyst which can recognize only one of the two mirror images of a chiral molecule. Okay, for example, we use a chiral catalyst that behaves like a right hand, right? Okay, it can only recognize another right hand, right? Okay, it cannot recognize, it will not react with, okay, will interact with the left hand, right? So that's a good analogy. And actually, Noah's used this chiral catalyst to make the so-called L-dopa selectively, okay? And this is the R-dopa, right? The R-dopa was not formed, okay, because he used a chiral catalyst, okay, that can go straight to make the L form, okay, and leave out the R form, okay, and the L-dopa form is used for medicine for treating Parkinson's disease, and the D-dopa does not have this pharmaceutical effect. Okay, and then only 4 years later, another Nobel Prize for catalysis came out this time. Okay, it went to those three chemists. The French chemist Xi'an, the two American chemists, okay, Robert Grubbs and Dick Schrock. Okay, actually I met both of them, talked to both of them. So they got their Nobel Prize in chemistry for developing the so-called metathesis method in organic synthesis. Okay, the word metathesis comes from Greek, okay, which means exchange. Okay, so this reaction is catalyzed by, of course, transition metal complexes. Okay, so the reaction is known as an olefin is known as a change your partner stance. Okay, metathesis. You see, it can make the two olefin molecules exchange their parts, right, around the carbon-carbon double bond. Okay, you get A, B, okay, and a BA, right? This is a great discovery, okay, because this reaction can be used to make a lot of value-added chemicals. All right, here's the 7th Nobel Prize for catalysis that was awarded 5 years later. So this time, the transition metal element is palladium. Okay, so palladium is called the king of transition metal catalyst. It won this Nobel Prize for those three chemists, right? Okay, because they developed palladium catalyzed cross-coupling reactions that are widely applicable to many kinds of organic compounds. Okay, so these so-called cross-coupling reactions, 交叉偶联反应, okay, are capable of constructing new carbon-carbon bonds, okay, to build up molecular complexity. Because as we all know, organic compounds are carbon-based, right? Okay, if you want to do organic synthesis, you need to make a new carbon-carbon bonds, right? Okay, these palladium catalyzed cross-coupling reactions, okay, do the best work on making new carbon-carbon bonds. Okay, and only a couple years ago, okay, the 8th Nobel Prize for catalysis was awarded to Benjamin List and David Macmillan, the German chemist, this the Scottish-American chemist. Okay, you see what a contrast, okay, the two faces, the smiley face, you see this very serious face. This time you see no transition metals this time, okay? It's pure organocatalysis, okay? It's supposed to be This chemistry is supposed to be greener because it's all organic, okay, no metals involved. So this is the first generation Macmillan catalyst. Okay, he actually developed this new catalyst by chemical synthesis. And Benjamin List used a naturally occurring known substance as his organic catalyst. Okay, there's L-proline. Okay, here's a summary. So these recent Nobel Prizes for catalysis were awarded to those chemists who developed homogeneous catalysis. Okay? In a homogeneous catalytic reaction, the catalyst and the reactants are all dissolved in the same liquid phase, liquid solution. Okay? Generally, homogeneous catalysis offers a better control of the products we want to make. In addition, homogeneous catalysis provides a better opportunity for us to look into the deep mechanism of a catalytic reaction. So for the past 10 years or so, okay, I've been doing computational catalysis, okay, which is, we use computational tools to study homogeneous organic reactions catalyzed by transition metal catalysts. Of course, okay, these reactions are potentially useful for organic synthesis. So computational catalysis was a term, okay, coined by a few experts about 10 years ago. Okay, it is actually just a study of catalytical mechanism by computational modeling. Okay, the good thing about computational catalysis is it is especially useful for catalytical reactions where the intermediate species are too reactive to be observed by experiment, because a lot of chemical reactions are very fast, right? The intermediates, okay, you cannot be dictated or studied by experiment. Okay, that's why computational catalysis can play a critical role in revealing the detailed workings of a catalytic reaction. That's the area I have been working for the past 10 or so years. Traditionally, theory and computation have provided a supporting role in explaining experimental facts, right? But nowadays, okay, computation theory and computational modeling can do much more than just interpreting experimental facts. It can discover new chemistry. It can predict experimental outcomes. It can be used to design new molecules and new chemical reactions, and it can inspire new ideas, okay, for experimentalists to do more, to develop new reactions. Okay, now our interest in transition metal catalysis cover these fundamental bond-forming and breaking reactions, including alkene carbon-carbon double bond metathesis, also known as olefin metathesis, carbon-carbon cross-coupling reactions, and carbon-hydrogen bond activation and functionalization reactions. We have studied both precious transition metals and earth-abundant transition metals. So these are a list of precious metals. You see ruthenium, rhodium, palladium, silver, gold. Okay, these are expensive precious metals. By contrast, we have these so-called earth-abundant transition metals that are much cheaper, okay, and more widely available. Okay, that's titanium, okay, nickel, cobalt, copper, okay, Now I'm going to show you some examples of my work. I try to I try to speak in a way that is understandable to you, but now let's see how it goes. All right. So this is the first computational catalysis project I took on. Okay, Grubbs is extension of and a development of his Nobel Prize winning work. So I read this experimental paper in the Journal of American Chemical Society, in 2011. You see this reaction is catalyzed by the so-called fourth generation Grubbs catalyst. It is capable of producing the Z isomer in 95% yield. The first 3 generations could only produce a mixture of both cis and trans isomers in approximately equal amounts, like 50-50, right? This catalyst is so-called stereoselective catalyst, and it can be used to make complex natural products and stereoregular polymers. That's why this was was called one of the top 10 breakthroughs of chemistry of 2011. I read this communication in JAX, and I said to myself, I'm going to use computational tools to look into this reaction, trying to explain why this reaction is Z selective. So what we did was to find a new reaction pathway for this catalyst. This so-called the bottom bond olefin attack works for the first 3 generations of Grubbs catalyst. It does not work in this case. What we found is so-called side bond. The side bond olefin attack. So this opens up a new reaction pathway that is stereo selective. That is Z selective. As you can see, we found the 2 energy barriers for the Z product and the E product. You see the gap between the 2 energy barriers is in other words, the Z barrier is lower than the E barrier by 2.2 kilocalories per mole. We can plug this number into the equation to calculate theoretical selectivity, 97%, which agrees well with the experimental reported selectivity, 95%. So it was pretty good, And then we also studied palladium catalyzed cross-coupling reactions in general, and the so-called Suzuki cross-coupling reaction in particular. So the Suzuki cross-coupling reaction is the most widely used cross-coupling reactions in organic chemistry, organic synthesis. That's why people are still working on this reaction, trying to come up with new variations. And this new development says, report says they found a so-called palladium-2 only mechanism. We did extensive computations on this reaction, and our results indicated there's actually a hidden palladium-0 generating process, and a favorable palladium-0, palladium-2 mechanism thereof. So basically, we corrected their misconception. All right. We also studied transition metal catalyzed carbon-hydrogen bond activation and functionalization, because we all know carbon-hydrogen bonds are everywhere in organic compounds, organic materials. Therefore, if we can activate carbon-hydrogen bonds and convert them into other value-added chemical functionals, functional groups, and then it will have enormous economic implication. And Jing Kuan Yu has been a leader in this field. Okay, this is taken from his website, and I actually met him at a Gordon conference some years ago. I was a little younger, right, back then. So I started watching the papers coming out of his research group, where at his peak time, his group could publish a paper in Science, Nature, or one of the top chemistry journals every other week. Okay, that was just amazing. That was amazing. And luckily, I read this paper in Science. Okay, it was considered a breakthrough in CH bond activation and functionalization chemistry. So I called him. I said, Jing Kuan, I'll try to study, to compute your reaction, trying to explain why you observed this intermediate A. They actually isolated this intermediate and got crystal structure of this molecule. Okay, I said, okay. Jing Kuan was very supportive, very helpful. Okay. He said, well, he would support us, and I actually discussed some questions with him on the phone as we were working on this project. So we were able to illustrate the detailed mechanism of the reaction computationally. So they got their paper in Science. We got our paper in the Journal of American Chemical Society. Not bad, not bad. But even better is we found something they missed. Okay, our calculation indicate there should be another isomer of A. They reported A, right? They isolated this intermediate A. Okay, but according to our calculations, there should be this, the isomer B that should be isolated alongside A, because they are almost have the same energy, and then they can interconvert in solution, by overcoming a very small barrier. You see 14.5 kcals per mole is pretty small for room temperature. Did they miss B? Yes, they missed B. Okay, we got the crystal, the single crystal file from the journal Science. Actually, I sent an email to the editorial office, and they sent me the CIF, the crystallographic information file, and we analyzed the CIF, and indeed, it shows both A and B in there, but they missed the B. Okay, they only got A. Okay, well they were good. They appreciated our work, and they didn't get angry. They're good. They're good scientists. All right, nickel is an Earth's abundant metal. It could dethrone palladium, the king of transition metal catalysts, for several reasons. First of all, nickel is a lot cheaper than palladium. Okay, I got this price quote a couple of weeks ago. You see, palladium is nearly 2,000 times, right, more expensive than nickel, right? Okay. They're next to each other, in the periodic table. They're in the same family, nickel just on top of palladium. Cost is not the only factor. There are other important factors. Nickel has unique chemical properties that are different from those of palladium. Therefore, the chemistry of nickel is different from that of palladium. So we can use the unique chemical properties of nickel to develop catalytic reactions, that cannot be achieved by using palladium catalysts. The best example is known as the reductive cross-coupling reaction, catalyzed by nickel complexes. It was developed by my collaborator, Professor He Guigong of Shanghai University, and a few others. So the good thing about this method is it is capable of coupling two so-called electrophiles directly, to form new carbon-carbon bonds. This is better than the traditional palladium catalyzed cross-coupling reactions, which have to convert one of the electrophiles into a nucleophile, to form an organometallic reagent. So we, in collaboration with the Gong group, we kind of did some work on sp2 carbon, sp3 carbon reductive cross coupling. And then we are continue our collaboration. We are working on the more challenging sp2 carbon, sp2 carbon, and sp3 carbon cross coupling reactions. Okay, let's keep our fingers crossed. So hopefully we'll have good news to report to you before long. Okay, and cobalt, you see cobalt is, where's cobalt? Cobalt is next to nickel in the periodic table, right there. Okay, cobalt is another Earth abundant metal, okay, very useful catalyst material. Okay, we studied the cobalt catalyzed hydroformylation known as the oxo process. This was the first industrial scale reaction by homogeneous transition metal catalysis. It is one of the most studied and used catalytic reactions. Okay, worldwide, there is more than 10 million tons of products that are made by this catalytic reaction. Okay, it converts an olefin carbon monoxide and hydrogen gas, three-component reaction. It converts the three components into useful value-added chemicals known as aldehydes. Okay, construction materials. Okay, 装修材料 aldehyde 醛. Okay, and aldehydes can be used to be hydrogenated to make alcohols, which are used as plasticizers for PVC and SAS for detergents and cleaning agents, and as solvent for or further processed to form polymers. Okay, and it's also used to make specialty chemicals relevant to organic synthesis of a fragrance and natural products. It's a very useful reaction, and this reaction was originally catalyzed by this cobalt complex. Okay, and then they used rhodium catalysts that are more efficient for the industrial processes. But the thing is, rhodium is one of the most expensive precious metals, very expensive, right? And then the chemists at Louisiana State University came up with a cationic cobalt catalyst. Okay, the original cobalt catalyst is a neutral, charge neutral compound. Then they use these cation catalysts to dramatically increase the efficiency. Okay, so they're almost as good as rhodium-based catalyst. And we read this paper in Science, and we did computational work to illustrate the detailed mechanism of this reaction. Okay, among our important findings is the barrier for the activation of the catalyst. Okay, 33.8 kcals per mole, which is pretty high. That's why this reaction requires, higher than 100 degrees C to do the reaction. And we did some computational modification of the catalyst system, and our calculations indicate we could, with these moderations, we can lower the barrier to 31.1 kcals per mole. So it's pretty small, right? Only 2.9 kcals per mole, right? But the relationship is exponential. We can actually, the rate of reaction would increase by 94 times. Okay, if this could work experimentally. So actually, I sent our results to the experimentalists. Okay, so hopefully you can try this to get to improve this important catalytic reaction. Okay, so with that, I'm going to do this little summary. To promote catalysis. Catalysis makes the world a better place. So catalysis makes chemical reactions easier, faster, and possible. Catalysis powers chemical synthesis that makes pretty much everything that supports our modern way of life. Medicines, advanced materials, polymers, and so on and so forth. Applications of catalysis have been so far dominated by transition metal-based catalysts. But hopefully things will change, okay, as more and more organic catalysts and biocatalysts are being developed, okay, and commercialized. Sustainable and green catalysis are being developed that use Earth's abundant metal catalysts and organic catalysts. And lastly, catalysis keeps rocking the world. 催化不断给我们世界带来惊喜。Thank you all for your attention. Okay, I need to acknowledge support for my work from the National Science Foundation of America and the Supercomputing Center, Colgate Company, my previous university, and XATLU, and the Hoffman Institute of Advanced Materials in Shenzhen, where I worked for 2 years as visiting professor, and I'm indebted to many talented co-workers. Okay, they made all my research possible, and there's a special thanks to Rolf Hoffman, who got the Nobel Prize in Chemistry in the early 1980s. Okay, I call him Uncle Rolf, okay, because he and my PhD advisor were both working for Lipscomb at Harvard University, so I call him Uncle Rolf, 师叔, okay, because Hoffman started the field of computational study of chemical reactions. Okay, thank you for your attention. I'll be happy to answer questions. Thank you.
Thank Professor Wang for taking us through the amazing journey of those exciting research on catalysis. So now we would like to open the floor for questions and discussions, and we welcome questions from the audience, both on-site and online. If you have any questions, please raise your hand, signal. Yes, please.
Professor Wang, thanks for that great talk. So can you open up the black box of catalysis computation a little bit more? How is this different from a typical molecular modeling, let's say a protein structure?
Well, basically there are two approaches. There's the computation based on quantum mechanics. There's the computation based on molecular mechanics or Newton mechanics. Okay, what I'm doing is quantum chemical calculation based on density functional theory. Yeah, it is based on quantum mechanics. That's the major difference. I think for most of for the computation big biomolecules, most of the people mostly use molecular okay, known as calculations. Yeah.
Quantum chemistry is much more difficult to understand.
Well, but the thing is, there is so-called QM method that is, that is very promising. With this hybrid method, you can model the core of your system, okay, a small core with like 100 atoms using quantum mechanics, and then you can model the big biological pocket with using molecular mechanics.
Okay, so a follow-up question: if you use catalysis computation to study how enzyme works, would you still be able to?
There are different approaches. I have never done that, but I'm aware, okay, how that has been done. The best approach is to use the so-called QM method.
So it's sort of hybrid.
Yes,
method.
Yes.
Okay. Thank you. Thank you very much.
So thank
Hi,
you for your
Jiren.
time, Professor Wang. As you have mentioned both experimental stuffs and the computational stuffs, I am interested in how can you tell people which catalyst is efficient experimentally? Like how do you design a good catalyst experimentally?
Okay, very good question. First of all, you need to have mechanistic understandings, right? For example, we calculate the activation of the so-called pre-catalyst, right? We calculate the barrier. We found out how the catalyst was activated to become an active species, right? And then we can try to modify the catalyst by changing the function, or changing some atoms and groups to see if that can lower. Okay, we're going to use the chemical. Of course, we need to use chemical intuition and chemical principles such as electronic effect, the steric effect, and the non-covalent interactions. And then we can calculate the barrier. Okay, and the barrier is indeed becomes lower. And then we need to communicate the idea to experimentalists to see if they can give it a try in the lab. That's the approach we've been using. Yeah, mechanistic understanding is the basis. You need to understand the mechanism first.
Okay, so a follow-up question. So right now in your field, like the development of mechanism and like some guidance of design new catalysts, which one is dominated? Like there is an existed catalyst and you want to verify the mechanism of the process and you can also come up with new catalysis.
Yes, right now it is well. So your question boils down to interpretation versus prediction, right?
Yes.
I would say right now, okay, interpretation is still, more kind of more, more important than prediction. But the prediction is becoming increasingly useful. That's the that's direction of the field.
And another question, because the experimental conditions and the things that you can change in the computational modeling are not always the same, because sometimes the solution is a very complicated system. So sometimes it may exist like your method based on quantum mechanics calculation is useful, but it may fail in the experiments. So
it is possible, yeah, because theory must be checked with experiment. Yes, I agree with you totally. That's why our computation work is closely related to experiment. Yeah, we need to check our computational results with experiments. Yes. Yeah, we can use known experiments to try to study mechanisms. In the hope of gaining novel insight into the course of a reaction, and then we can kind of come up with some ideas. To try to modify the catalyst to see if we can make the reaction more efficient. As you said, the reaction conditions can be complex, right? But when you can only change one thing at a time. Yeah. So when I choose a system, a catalytic reaction to study, I want the reaction to be well defined, clean, so-called clean reaction. I don't want to study reaction where they add too many different, substances or additives. That will make the mechanistic study very difficult.
And also, sorry, I have a lot of questions.
No,
so
no
based
problem.
on my previous experience and knowledge, quantum mechanics calculations always based on one or two molecules. So what will happen if there are like a large amount of molecules? So quantum mechanics may not be very sufficient for such.
Well, okay, QM calculations can be applied now to both so-called discrete molecular systems, like what we are doing, okay, isolated molecules, right? It can also be applied to extended systems like solids, because the VASP algorithm is very good at modeling extended infinite systems. There are ways of calculating infinite structures with quantum mechanics based approaches.
But need time and money.
But I'm not expert. I don't know how to. I do isolated. I calculate do DFT calculations on isolated molecules.
Okay, thank you for your time and answers.
Thank you for your questions.
Hello, Professor Xiaotai Wang. This is actually a very impressive presentation. I'm not
Thank
a
you.
person in this field. I saw the topic is catalysis makes a world a better place, right? I'm wondering, are there any catalysis scenarios can make the world bad or worse? I'm not sure. Just maybe this question sounds not that like expertise, but just curious.
Okay, we need to. Okay, we need more than science and scientists to make the world a better place, right? Okay, we need good policy making, right? Okay, let me. Yeah, some of the industrial scale catalytic reactions may have may cause some negative effects. Yeah, but I think the positive effects, kind of outweigh the negative effects, I would say.
Dr. Wang,
Yeah.
now the AI is a very hot topic because you are doing computational catalysis. Do you think the AI is going to play a role in this field? And just curious.
To some extent, like my friend Hong Xin, Professor Hong from Zhejiang University, I invited him to visit our department. Right, he is an expert in AI, in machine learning. So their group is trying to to come up with AI-assisted approaches to computational findings. Okay, I think it will be useful to some extent, but I don't think it will replace humans totally in the foreseeable future.
Thank you.
Let's thank Professor Xiaotai Wang for this wonderful talk.
Thank you.